All right, hi everyone, this is Professor Oaks, and this video is about power series. So, what is a power series? Well, a power series is an infinite series of this form here. All right, so you can see it's a sum k equals 0 to infinity of ck times x minus a to the k power, and then if you write it out in expanded form, this is what you get. So this is a power series in x minus a. So here's the x minus a that we're talking about. And it's sometimes called a power series centered at a or just a power series. And these constants, C0, C1, C2, C3, are the coefficients of the power series. And so x is a quantity that can vary at will, with the series converging for some values of x but not for others. So here are a couple of special notes. If x is equal to a here, then we have the series that is just going to be, all right, now think about it. This is, if x is equal to a, we have ck and then a minus a to the k. So what you want to remember then is that we're going to, by definition, just take this to converge to C0. All right, so even though a minus a is 0, we're going to, by definition, just say that this is converging to C0. Now, if you look at this, if you expand out the terms, that's what happens, because all the other terms are 0 except for this first term. Now, if a is equal to 0, then this here becomes ck x minus 0 to the k. And so then the series, because all the a's are 0, reduces to this. And that's just called a generalized polynomial in x. So then the set I of all numbers x for which a power series converges is called its interval of convergence. And again, remember that what I said here is true, that for some values of x, this series will not converge, all right? So we have to give the interval of convergence of x values for which the series will converge. So here are the different cases here. This set I is a bounded interval with center A and endpoints a minus r and a plus r, where r is a positive real number called the radius of convergence of the power series, and the endpoints may or may not belong to R. However, the power series always converges absolutely on the open interval a minus r to a plus r. So that means that we are going to need to check the endpoints here, because the series may not converge at the endpoints of the interval. And then case 2, on the unbounded interval negative infinity to infinity, the radius of convergence is infinite, so r is infinity, and the set I, or the interval I, consists of a single number, and then r would be 0. So either r is a positive real number, r is infinity, or r is just 0. All right, and again, because this is a radius, of course, hopefully you're already thinking in your head that it wouldn't make sense for this to be a negative number. So how are you going to find this radius of convergence? All right, so if this is a power series with radius of convergence r, suppose that the limit as n goes to infinity of the absolute value of c n plus 1 over cn is equal to L, where L is either a non-negative real number or L is equal to infinity, then if L is a positive real number, then R is equal to 1 over L. If L is equal to 0, then R is equal to infinity. And if L is equal to infinity, then R is equal to 0. But this theorem does not apply if the limit does not exist. So if the limit doesn't exist, then the theorem does not apply. However, it doesn't mean that the radius of convergence doesn't still exist, because here's an example of like where the radius of convergence may still exist. All right, so keep that in mind as well. So remember, L has to be a positive real number, L has to be 0, or L has to be infinity for this theorem to find the radius of convergence to work. So let's find the radius of convergence for this series right here. So we have k factorial x to the k. So I can rewrite that as k factorial and then x minus 0 to the k. And I'm doing this just so that as we're starting out, you can identify what ck and the a is. So ck is k factorial and a is 0. So if we want to find the radius of convergence, we need to figure out the limit as n goes to infinity of the absolute value of Cn plus 1 over Cn. And then here we go. So Cn plus 1 is n plus 1 factorial, and Cn is n factorial. So this limit is limit as n goes to infinity of the absolute value of n plus 1 factorial over n factorial. So it's a limit as n goes to infinity of, all right, n plus 1 times n factorial over n factorial. So the n factorials divide out. So this is the limit as n goes to infinity of n plus 1, and that will be infinity. So since L was equal to infinity, that means that the radius of convergence is equal to 0. So since L was equal to infinity, the radius of convergence is r equals 0. So what a time to be alive. All right, so let's try another example here. So here is the series. So we have ck is 3 and a is, well, that will be 2 here. All right, so that means Cn plus 1 is 3, and Cn is 3. So we need to find the limit as n goes to infinity of the absolute value of Cn plus 1 over Cn. So it's a limit as n goes to infinity of the absolute value of 3 over 3. So that will be 1. And then since the L equals 1 is a positive real number, the radius of convergence is going to be, r is, remember, it's 1 over L, so that's 1 over 1, so it's 1. So r is 1 in this case. All right, let's try another one here. So this one isn't actually necessarily as clear of the fact that it's in a power series form, but we can rewrite this. So just so that we're very clear on this, so I'm going to rewrite this sum 0 to infinity, negative 1 to the k over 2k plus 1 factorial, and then x to 2k plus 1. But remember, I just want the series to be of the form a ck x minus a to the k power. But right now, this is x to the 2k plus 1 power. So how am I going to actually rewrite this? Well, I could actually let a w be 2k plus 1. And so that means that w minus 1 is 2k, and then W minus 1 over 2 is equal to K. All right, so this can be rewritten some K equals 0, well, W, because we're using W's. So when let me rewrite this so that you can see it a little bit more clearly here. I'm trying not to use a regular pen here just because I don't feel like it shows up as well in the videos, but if I have to, then I will, but I don't know why this whiteout is a ripoff here. So this whiteout, by the way, is not very good. So just so that you know, like, I would not buy this particular whiteout again if I had a choice. Cause look at it, it's not even doing what it's supposed to. So actually, now I think it's going the wrong way. So anyway, just remember that we're trying to write this in power series form here. So here we go. Actually, it's working. The whiteout is working now, but it's actually not covering anything up, which I find is actually even more strange. So I guess we will just, I digress at this point. It's fine. I mean, as long as you can see it at this point. All right. So W is equal to, now remember, when K was 0, then what actually happens is that W is equal to 2 times 0 plus 1. So it's actually starting at 1 now and going to infinity. So just remember, this is from 1 to infinity now and not from 0 to infinity. All right, now the K was W minus 1 over 2. So this will be negative 1 to the W minus 1 over 2 power, and then over 2K plus 1 factorial. So W was 2K plus 1, so W factorial, and then X to the W. And then I can rewrite this as my CW. So that's negative 1 to the W minus 1 over 2 over W factorial. And then this here is my X minus 0 to the W power. So A is 0. So this is a power series. And so now all I need to find is going to be, right, limit as n goes to infinity of, now that will be the Cn plus 1 over Cn. And remember, I'm using this series here. So this is the limit as n goes to infinity of, and that will be a negative 1 to the n plus 1 minus 1 over 2 over n factorial, actually n plus 1 factorial, all over negative 1 to the n minus 1 over 2 over n factorial. And because this is absolute value, I don't need the negatives anymore. So it's limit as n goes to infinity of just 1 over W plus 1 factorial times the reciprocal, or n plus 1 factorial, and then the reciprocal of the denominator, n factorial over 1. So this is limit as n goes to infinity of 1 over n plus 1 times n factorial over 1. The n factorials divide out, so it's limit as n goes to infinity of 1 over n plus 1, and that goes to 0. And so since L is equal to 0, the radius of convergence is going to be R is equal to infinity. All right, what a time to be alive. So I really hope that you enjoyed that. So let's go ahead and do a few examples now of how we would find the interval of convergence. All right. So now we're going to find the interval of convergence. Here we go. So now remember that there are a few things that could happen. All right, if in case 1, R was 1 over L, then the interval would be either A minus R to A plus R, or it could be, uh, well, it could converge at A minus R, but not at A plus R, or it could converge at A plus R, but not A minus R, or it could converge at both endpoints. All right, so now remember the other thing that could happen is that R could be infinity, and so then the interval of convergence would be negative infinity to infinity, or R could be equal to 0, which means that the interval is a single number. All right, so just it's not even really an interval, it's just the set that the series converges on is just a single number in that set. All right, so let's look at this first series and find the interval of convergence. So I know that the ck is 1 over k, and then, so if I rewrite this, all right, as 1 over k times x minus 0 to the k, then I know that the a is equal to 0. So Cn plus 1 is 1 over n plus 1, and Cn is 1 over n. So the limit as n goes to infinity of the absolute value of Cn plus 1 over Cn is the limit as n goes to infinity of the absolute value of 1 over n plus 1 over 1 over n. So that's the limit as n goes to infinity of the absolute value of 1 over n plus 1 times n over 1. And so that ends up just being 1. And so since the L is equal to 1, the radius of convergence is going to be, all right, so the radius of convergence is R is equal to 1 over L, so that's 1 over 1, which is 1. So R is equal to 1. So then I know for sure that the the series converges or converges absolutely in the open interval. So in the open interval of a minus r to a plus r, but a was 0, so 0 minus r, which is 1, and 0 plus 1, which is 1. So negative 1 to 1. But now I need to check the endpoints. So now check the endpoints. So I need to check at what happens at x equals negative 1 and at x equals 1. So remember the series was k equals 1 to infinity of x to the k over k. So when x is equal to negative 1, I have sum k equals 1 to infinity of negative 1 to the k over k, and then this is actually the alternating harmonic series. So this is the alternating harmonic series, and the alternating harmonic series actually converges. So that means that I have to use a bracket here at negative 1. All right, so that means a bracket at negative 1 because to indicate that negative 1 is a value for which the series converges. And then I'll check when the x is equal to the other endpoint, the 1. And so that's sum k equals 1 to infinity of, well, 1 to the k over k. And this is the harmonic series. So that's a harmonic series, but that diverges. So that means, remember, I need to use a parentheses to indicate that negative 1 is one of the values for which the series actually does not converge, but a bracket at negative 1 to indicate that it's one of the values for which the series does converge. So since the series converges when the x is equal to -1, but diverges when x is equal to 1. That means that the interval of convergence is going to be, all right, -1 to 1. So hopefully you enjoyed that. So let's try another wonderful example here. So let me get this one together, and this will be our last example on finding the interval and radius of convergence here for these power series. So now what do we need to do here for this one? So let's look at this here. All right, so I know that if I look carefully at what's going on here, I have a CK that is equal to, so CK is equal to -1 to the K over 2 to the K, or I could just rewrite this as a -1/2 to the K, and then the A is going to be -1. All right, so this was x minus a -1 to the K power. So A is equal to -1. So now we need to find the radius of convergence. So Cn plus 1 is -1/2 to the n plus 1. Cn is -1/2 to the n. So the limit as n goes to infinity of the absolute value of Cn plus 1 over Cn is limit as n goes to infinity of the absolute value of the -1/2 to the n plus 1 over -1/2 to the n. So that will be limit as n goes to infinity of the absolute value of, actually, well, that's just going to be -1/2, which is 1/2. And so since the L here is equal to 1/2, that means the radius of convergence is going to be, right, that will be R is 1 over L, so 1 over 1/2, which is 2. So therefore, the series actually converges in the open interval a minus r to a plus r, and a was -1 and r was 2. So we have that the series converges in the open interval -3 to 1. Now again, after that, we need to check for convergence at the endpoint. So now check for convergence at the endpoints. So let's do that here. So at x equals -3, remember that the series was k equals 0 to infinity, and then I wrote it as -1/2 to k, and then x plus 1 to the k. So if x is -3, I have sum k equals 0 to infinity, -1/2 to the k, -3 plus 1 to the k. So that's k equals 0 to infinity of -1/2 to the k, -2 to the k. So then if I multiply this together, this is sum k equals 0 to infinity, and that's just 1 to the k. And so this is actually just 1 plus 1 plus 1 plus 1, etc., until we add it up and we see that it diverges. So now we need to check at x equals 1. So that's the sum k equals 0 to infinity, -1/2 to the k, and then we have 1 plus 1 to the k. So that's sum k equals 0 to infinity, -1/2 to the k times 2 to the k. So that's sum k equals 0 to infinity. If I multiply those together, it's -1 to the k. So we see it's -1, and then well, 1. All right, 1 plus -1 plus 1 plus -1, and so on. So we see that this one also diverges. And so therefore, since the series diverges at x equals -3 and at x equals 1, that means that the interval of convergence is just going to be -3 to 1. All right, so I really hope that you enjoyed that. That is the interval of convergence for this power series here. So, unfortunately, that is all I have for you on power series. So, thank you for watching, and I hope that you are already looking forward to the next video. Thank you, and have a great day.